Hello again and welcome to section 2, momentum and the impulse momentum theorem. So, last time we talked about what impulse was. Impulse is simply the area under a force versus time graph. So it's the average force applied during a collision times the amount of time, the duration of the collision. As it turns out, the impulse here on the left-hand side of this equation, this is J, is equal to the change in the mass of an object times its velocity. Now, we saw before that we had a hockey puck hitting or being hit by a hockey stick. And we can imagine if we saw that in real life, we would see that the speed or the velocity of that hockey puck would inevitably change. And the amount by which it changes is the mass times the final velocity minus the mass times the initial velocity. The mass times velocity we're going to call momentum. Momentum, it has the symbol P because M has been taken already with mass. And so impulse, we can rewrite this another way. Impulse is equal to final momentum minus initial momentum. And impulse is in fact a vector. Here we have it rewritten at the bottom. So impulse, which is equal to the average force times some time interval, is equal to the change in an object's momentum. Now, generally speaking, what is going to change about an object is the velocity, but sometimes in more advanced problems, we'll see that, in fact, the mass can change also. So let's talk more about this. So the impulse momentum theorem, here we have, again, the hockey puck being hit by, well, okay, in this case, it's a golf ball, hit by a golf club. So the club, we say, delivers an impulse to the ball, which changes the ball's momentum, right? Initially, the ball was at rest, and finally, it has some momentum. If we were to look at this with vectors, in vector notation, the impulse was to the right, the initial momentum was 0, thus the final momentum has to be to the right. We can make it a little more complicated, which maybe will be a little more clear. Say we have a soccer player heading a soccer ball. The ball has initial momentum down toward the guy's head. The guy's head delivers an impulse, a force with some duration, in the direction up and to the left. The final momentum, we can figure out its direction using vector math. So here we have P final is equal to P initial plus the momentum, right? Before we had the impulse is equal to the change in momentum, or final minus initial, right? So if I want to know the direction of the final momentum, that's equal to the impulse plus the initial momentum. And that's the what we see graphically right here, right? We start at the dot. Our initial momentum points down and to the left. The impulse is up and to the right, right? Add those two vectors up, and here we see the final momentum of our soccer ball. Okay. So let's now use this information to find the approximate speed of that same hockey puck that we had earlier. Let's remember our answer to part A, the average force was 25 newtons. The impulse on the ball we calculated to be half 0.5 newtons times seconds. Now we saw that the units could also be written as mass time, kilograms times meters per second. Now we go back and take a look at momentum. Momentum was mass times a velocity. We see that the units will also work out. So now we want to find the final speed. So V final is equal to what? Now for these problems, this might be a little overkill for this simple one, but we always want to draw a picture. So here's my hockey puck with some mass M and some initial velocity I. Now it says that the impulse is delivered to the hockey puck, but it doesn't say in which direction. So we're going to assume this is a one-dimensional problem. This is a positive force. So we'll assume that the force is being applied in the positive direction. So here we have an impulse J being delivered. Okay. So the final velocity we would expect to look like what? Well, if we're hitting a hockey puck that's already going to the right, we hit it to the right, the final velocity, here's our mass m, should be even larger than the original and also to the right. Okay, so we can calculate that mathematically. We know that the impulse is equal to the final momentum minus the initial momentum. On the left-hand side, we have the average force. Well, actually, I've already calculated the impulse, so I don't need to do that. So we're going to solve for the final momentum, and I can get rid of the vectors now because they're all positive, is equal to j plus the initial momentum. The final momentum is m times v final. That's equal to the impulse plus m times v initial. So I'm going to divide everything by m. So v final is equal to the impulse plus my mass times initial velocity over the mass again. Now I can plug in numbers. The impulse I had before, half a kilogram times a meter per second, 0.5 kilogram times meters per second, plus the mass of my hockey puck, which was half a kilogram, times the velocity. The initial velocity was 10 meters per second, moving to the right. Oops, too far. Should be 10 meters per second. Sorry, I ran out of space a little bit. All of that divided by 0.5 kilograms. Okay, this one I think I can do in my head. Half of 10 is 5. 5 plus 5 is 5.5. So 5.5 divided by 0.5 is 55 divided by 5 is 11. And let's take a look at the units. Kilograms on top cancel with the kilograms on the bottom. And we're left with just meters per second. So the final velocity is 11 meters per second. And we think about that for a minute. Well, my initial velocity was 10 meters per second. So yes, in fact, this is a number that is larger than the original velocity. So that seems reasonable. Check. Good. Okay, so this impulse momentum theorem also applies to things where the final momentum is zero. For example, when you're jumping off of, a ledge and you land, well, when you land, your final momentum is zero, right? You're landing, you're coming to a stop. As you jumped, right here you are jumping from some ledge. Of course, you're going to do this safely, right? There you go. If you think about how you land safely on the ground, you typically bend your knees and you, one would say, absorb the shock, if you will, right? So here my final momentum is equal to 0. And the reason why you bend your knees is because you're increasing the duration that the force between the floor and your knees is being applied. Okay, so let's go through this equation right here. So your impulse, the impulse on your body when you're jumping off of a ledge is equal to the average force being applied, the normal force from the ground, times the duration of the collision. If your final momentum is 0, then this is all, the impulse is equal to the negative of your initial momentum. So here we see, right, we're taking this one and this one. If we increase the duration of the collision, we decrease the average force being applied to your body, and that makes it hurt less, right? If we decrease the average force, right, so we're increasing the duration, decrease the average force, that one goes up, this one goes down. If we decrease the average force, from Newton's second law, if the average force goes down, our acceleration goes down as well, because our mass, of course, is constant. And this means we have less pain. Good, so real-life practical applications of physics. Can you believe it? We can make things a bit more complicated by having a system of many particles. For example, billiard balls. The idea of impulse and momentum has a lot of direct application to billiards, for any of you pool players out there. We can calculate the total momentum, P, of a system of particles or objects as simply the vector sum of all of the momenta of each one. So for example, for these 3 billiard balls going off in all directions, my momentum of the first one, right, start at the beginning, here's P1, we add that to P2, add these like vectors, add that to P3, and our total momentum is the vector sum of all of them. And we could find this mathematically by saying the total momentum in the x direction is equal to P1 in the x direction plus P2 in the x direction plus P3 in the x direction, and so on. You can add up all of the x components to find the x component of the total momentum. Likewise, we can do this in the y direction. The total momentum in the y direction is equal to P1 in the y plus P2 in the y direction plus P3 in the y direction, and so on. Good. I'll see you for the next section.